Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi ta'ala wabarakatuh, and very good day to all participants from this conference. My name is Muhammad Kamaluddin bin Abdul Hamid. I'm from University Malaysia Sabah, together with my two fellow friends from University Technology Malaysia. So I would like to present our paper with the title Energy Efficient Distillation Column Design for an Existing Sequence Using Driving Force Approach. The difference of this paper from our previous paper is basically we still use the same approach, which is driving force approach. However, the previous study more on resynthesizing the sequence, whereas in this case, we maintain the sequence and we redesign the individual columns. So I will talk more in detail about this after this. Ladies and gentlemen, as we know that distillation column sequence for multi-component separation is essential. It's an essential process for any of a chemical plant for the separation as well as for purification of condensable mixture. As we know that for a mixture, for a component, or multi-component that we want to separate, we want to purify at a certain purification specification. So we need to have not only one distillation column, but a series of distillation column in the form of sequence. Okay. However, this sequence responsible for the largest contribution of the total energy consumption of chemical processes due to their high energy demand, heat demands. A single column requires a lot of energy as well as a sequence. So that's why in this kind of research, we need to come up with one simple approach, such that how that we want to reduce the energy consumption for an existing distillation column sequence. So there are several methods, there are several approaches, such that designing new distillation column sequence has been developed by previous study, by previous researcher. However, one alternative and safe way is to make use the existing sequence rather than we create a new one. So that's basically the idea of this study. So we maintain the sequence, we just redesign the individual distillation column within the sequence, such that we're able to operate more efficiently, possibly with a certain minor modification. Ladies and gentlemen, allow me to describe or explain what have been done in our in this research in this area. So there are methodologies has been developed for designing energy efficient distillation column sequence, which is based on driving force approach. So what happened in this sequence? So for developing EEDC or energy efficient distillation column sequence, the existing sequence, which is mostly a direct sequence, need to be redesigned, need to be resynthesized into a new energy efficient sequence. So our group, we concentrate on applying driving force approach. So for example, Mustafa et al. 2014, they applied this energy efficient distillation column sequence using driving force approach for alcohol separation process, and they come up with about 60% energy saving. In addition, Zaini et al. 2015, 7% saving for multi-component aromatic mixture. And Zubi et al. 2017, 7.6% energy saving for azeotropic separation process. So this is example. This is 3 examples of energy efficient distillation column sequence development using driving force approach. The idea is basically like this. This is example. So we have a series of list of hydrocarbon components, and which basically has an existing sequence, usually it's a direct sequence. And for this kind of research, they need to reconstruct the sequence into driving force sequence or energy efficient distillation column sequence by constructing driving force curve for individual splitting of the component. Okay, once we have constructed this driving force curve, based on driving force approach, the highest curve means the easy separation. Once we have easy separation, then energy required to maintain the separation will be at the minimum, since the separation is quite easy. So if we separate this splitting first, the highest curve, which is representing a splitting, therefore the overall energy requirement for the sequence might be at the minimum. So for example, here we have about 10 distillation column, and the more you have the sequence, the more column that you have in the sequence, when you apply this driving force approach for a sequence, redesign a sequence or resynthesizing the sequence, you may have a more energy saving. For example, in this case, we have about 40% energy saving. Okay? The approach is quite easy. You simulate the existing sequence, construct a driving force curve, and based on this driving force curve, you come up with the new energy efficient distillation column sequence. And once we simulate it and we compare the energy, so mostly we have about for this case we have about 40% energy saving. So what's so special in this paper? So in this paper, we still use the same approach, which is driving force, but we use it to redesign or to design energy efficient column in the existing sequence, meaning that we maintain the sequence as it. Okay, if the existing is a direct sequence, so we maintain as a direct sequence. However, we redesign the column based on driving force curve. How we do that? So we explain one by one. So this is the idea, the rough idea, the brief idea about this. We have the existing sequence and we simulated it, and we have about 59.31 megawatt energy requirement. And after that, we redesigned the individual columns. So since we have a four component with a 3 distillation column, therefore we need to have a 3 driving force curve. At this driving force curve, we have several points. Based on driving force approach, we need to design the individual distillation column at the maximum point of the driving force curve, which is in this case study. In this study, at the point A, the idea is at the maximum point of driving force curve, the separation is the easiest, and the energy required to maintain the separation will be at the minimum. So we want to show that, we want to prove that when we design individual distillation column at the maximum point of the driving force curve, the overall energy for this new sequence or the existing sequence will be less than the existing one. In addition, also, we have several points which is not located at the driving force curve, which is not at the maximum, slightly below the maximum point, representing the design alternative for this individual column. And once we design it, then we do the simulation again, and we found out we have about the same existing sequence with the new design of the distillation column has about 57.13 megawatt energy saving, energy requirement, which have about 4% of energy saving. So this is the detailed methodology, the step-by-step. We have 4 steps here. So first step is basically to simulate the existing distillation column sequence, as well as using a shortcut distillation column design method in order for us to come up with the design value, which is refractory ratio and also feed stage for individual column. This is the feed condition data that we use in this study. From that, we obtain the sequence formation. In this case, we have a direct sequence with the sharp splitting separation. And then after that, we simulate the distillation column sequence, the existing distillation column sequence with the 99.9% energy product recovery. This is the existing sequence. Once we have simulated, then we come up with this energy analysis with 59.31 megawatt energy requirement. Okay, this is the first step, which is the simulation of the existing sequence. The second step, basically, to redesign the individual distillation column within the existing sequence. In order to do that, so we need to come up with the splitting value. Okay, so we have a 4 component, therefore we have we have 3 splitting value. Once we have this splitting value, then we can plot the individual driving force curve representing these 3 individual distillation column. And we take point A, which is at the maximum, point B and C, which is slightly below the maximum point as a design alternative. Then we plot this curve, individual distillation curve, distillation driving force curve together with the points A, B, and C for the individual design. This is example. This is a plot for driving force plot for splitting number 1. This is for splitting number 2, and this is for splitting number 3. Once we have obtained these several design, then we calculate the individual refract ratio, minimum refract ratio, real refract ratio, as well as feed location. Once we identify or justify the value, the product purity value. This is the value. This is the result for all the design available here for the feed stage and refract ratio. Then from this we resimulate. We resimulate all the individual design for distillation column within this existing sequence using a rigorous simulation design method. And we come up with this result value. And the idea here is we need to show that we need to prove that at the maximum point of the driving force design, energy for all these existing distillation column will be less, okay, or will be at the minimum. So we have a point AAA, meaning that we design these 3 distillation column at the maximum point of the driving force curve. And we have 57.13 megawatt energy requirement. If you look at other component or other design, for example, design BBB, design CCC, and other kind of alternative design, the value will be much higher than the existing sequence. Okay, so therefore, these results show that designing distillation column, individual distillation column at the in the existing sequence at the maximum value, maximum point of the driving force curve, produce less energy requirement for the individual distillation column. Therefore, the existing driving force the existing sequence will also have a less energy requirement. So the last step, basically, we do energy comparison. So we have value of the existing sequence, which is about 59.31 megawatt. And the best sequence, which is design AAA, have about 57.13 megawatt energy requirement, which is about a 3.68% energy saving or energy reduction. So as a summary, as a conclusion, so this paper proposes a simple approach to design energy efficient distillation column within the existing sequence. So accordingly, all the individual sequence distillation column in the existing sequence are redesigned using driving force approach, where we found out that the design at the maximum point of the driving force curve for each individual column, which is at the point AAA, produces energy efficient sequence with 3.68% energy reduction compared to the existing sequence. So I would like to acknowledge the University of Technology Malaysia for supporting this study, as well as all my team members. Thank you very much. Thank you for your attention. Wassalam.